product of your telephone number and the time of day is less than or equal to 1, congratulations, you're moving backward in time. If the sum of your number and the number you dialed is greater than or equal to 1, you've reached the math shop. Please leave a message after the tone.
Hey, Chrissy, this is your old pal, Cliff Gifford at Solid Gold C-Rock 740, where the hits just keep on happening. Hope you can come back to me real soon, because this DJ needs a little help. Yes, a little assistance with that math conundrum I told you about yesterday. Call me, Chrissy. I gotta know soon.
Hi, Christine. What's all this for?
Would you believe this is a math project?
Is it?
Well, sort of. It's also a year's supply of bioenergetic guinea pig food.
No, not another fad diet.
Not for me. It's for my little cousin's guinea pig, Garp.
Oh.
You know my other cousin, Sherry, the veterinarian?
Uh-huh.
Anyway, she told me about it, but it all has to be mixed, like, in the right proportions.
Well, do you have a recipe?
Sort of. Okay, I need twice as many apricot pits as banana chips and half as much oatmeal as alfalfa flakes, and the number of poppy seeds is greater than or equal to the number of chia seeds minus the number of walnuts.
There is math in there somewhere. I can smell it.
No, those are the banana chips.
No.
Oh, really?
The problem you've just mentioned can be solved using math. Systems of equations and inequalities, to be precise. Well, I'm teaching those concepts in this program.
Well, I smell a cue. Hi, and welcome to the Math Shop, where mathematics is just another part of everyday life. I'm Christine, and over there is my talented and usually helpful computer, Euclid.
In the NHL tonight.
Speakers off, Euclid. And this is my colleague, Kanwal, and together we are equal to anything.
Usually, we do inequalities too.
Yes, today we're dealing with equations and inequalities, solving them this time with graphs and algebra. And what are equations and inequalities, you may ask?
Well, you will often see mathematical expressions connected by an equal sign. Y equals 2x plus 4. Telling you that the two sides of the mathematical statement have the same value. Such statements are called equations. Inequalities are mathematical expressions too, but use different symbols, meaning less than, greater than, less than or equal to, and greater than or equal to. For example, if I only have $5 in my pocket, I can say that the cost of my lunch, C, has to be less than or equal to 5, unless Christine picks up the tab.
Dream on, Kanwal. But one other point before we start. Systems of equations involve solving two or more equations at the same time to answer a problem. The same goes for systems of inequalities. We'll show you. I have a great systems of equations problem to work on. I got it yesterday from my friend Cliff.
Okay, how does it go?
Okay, well, Cliff is a local DJ at a radio station here. Euclid, roll clip 1.
It's 1:28, and it's time now to see if you know.
Cliff's station manager has told them that they have to play 12 commercial spots during a 1-hour show, and the total commercial time has to equal 10 minutes, no more, no less.
And how long are the commercials?
Each commercial is either 30 seconds or 60 seconds long. What Cliff needs to know is how many 30-second spots and how many 60-second spots should he play. Oh, and he's on the air in like half an hour.
Gee, so I better get down to work.
Yeah.
Well, a problem like this can be solved graphically or algebraically. But before I apply either method, I have to find equations that represent Cliff's situation. So let's do that. First of all, I know that there are two types of commercials. 30-second commercials and 60-second ones. Let's assign some variables. X will represent the number of 30-second commercials, and Y will represent the number of 60-second commercials. But Christine, you had said he had to play a certain number of spots.
Yeah, that's right, Kanwal. He has to play a total of 12 spots each hour.
Then the first equation is the number of 30-second spots plus the number of 60-second spots. X plus Y equals 12. The other piece of information that I have is that the total commercial time is 10 minutes. There are X number of commercials, and I can say that the total time of those commercials in seconds is 30x. So I could devise an equation which states that the time of the short commercials, 30x, added to the time of the long commercials, 60y, equals 10 minutes. But let's make sure I don't get tripped up on the units. Right now I have seconds on one side and minutes on the other side. But the units need to be the same. I should either convert the seconds to minutes or the minutes to seconds. It doesn't matter which. So I'll change the minutes to seconds. Each minute has 60 seconds. Therefore, 10 minutes has 600 seconds. So now I have 30x plus 60y equals 600. And now there are two equations, a system of two equations, sometimes called simultaneous equations, because I have to find one solution that satisfies them both. However, this one equation has some big values in it, 30, 60, and 600, all multiples of 30. So I can divide this equation by 30 to make it easier to deal with. That gives me this, which works out to x plus 2y equals 20. Now, as I said before, these simultaneous equations can be solved either graphically or algebraically. Let's start with a graph. But remember, before we plot our graph, we should rewrite the equations in the slope-intercept form. Y equals mx plus b, where m is the slope and b is the y-intercept. This form of the equation will give us the information we need for each line. So x plus y equals 12 becomes y equals negative x plus 12. And x plus 2y equals 20 becomes 2y equals negative x plus 20. To solve for 1y in the second equation, I divide every term by 2 and end up with y equals negative 1/2 x plus 10. And now I have what I need to graph these two equations and see where they intersect. Christine.
Right, Kanwal. Euclid, execute graph mode. Remember, x is the number of 30-second commercials and y is the number of 60-second commercials. So Euclid has labeled the x and y axes accordingly.
Perfect. Let's graph the first equation. Now, to start, I want Euclid to plot the y-intercept, which in this case is 12. That means the coordinate is 0, 12. Then I plot another point using the slope, which is negative 1. So from the starting point of the y-intercept, I move down 1 and over 1. Then I join the points to graph the line of the first equation. Now, I do a visual check to see if that pattern repeats along the line. 1 down, 1 over. And it does. Again, 1 down, 1 over. It does. So, every point on this line satisfies this equation.
And now Euclid can do the same thing with the other equation.
Let's clear the line first. Euclid, hold that line in memory. We'll need it later. The y-intercept is 10, or coordinate 0, 10. The second point is determined by the slope of negative 1/2, which means I go down 1 and over 2. Joining these 2 points gives me the graph of the second equation. And every point on this line satisfies this equation. Now, let's look at these two simultaneous equations together. Euclid, bring our first equation back. When Euclid plots these two line graphs together, the only point that satisfies both equations is represented by the point of intersection, which has the coordinate of 4, 8. Therefore, Cliff will have to play 4 30-second commercials and 8 60-second commercials in the hour to make up his 10 minutes.
Should we check?
It's always a good idea to check. If I substitute these values into my original equations, I find that the expression is true in both cases, and that confirms my solution.
So, we hope you're watching, Cliff. That's your answer. But Kanwal, in math, there's usually more than one way of coming to the correct solution. You said that you could have worked this out algebraically as well, without plotting a graph.
That's right. In this case, it would go like this. Starting with the same two simplified equations, x plus y equals 12, and x plus 2y equals 20. I could proceed with something called the substitution method. In order to use this method, I have to isolate the variable in one of the equations. This gives me the algebraic expression that I can substitute into the other equation.
You mean you want to isolate either x or y on one side of the equation?
Exactly, and I could begin with either equation. Let me show you. This time I'll take the first equation and isolate the first variable, which is x. I subtract y from both sides of the equation, and x plus y equals 12 becomes x equals negative y plus 12. Now, I have a new pair of equations to work with. X equals negative y plus 12, and x plus 2y equals 20. And since x equals negative y plus 12, I can take negative y plus 12 and substitute that for every occurrence of x in the second equation.
Let me show you that on Euclid. He is very clever at this kind of thing. So now we have negative y plus 12 plus 2y equals 20. And what's most important is that there is only one variable in this equation, which means we can solve it.
First, I need to combine like terms. By adding one negative y to two positive y's, I get one positive y, or simply y. That gives me y plus 12 equals 20. Next, I subtract 12 from both sides, and I find that y equals 8. Now that we know that y equals 8, I can take that value and substitute in my first equation for every y, and then solve for x, like this. If x plus y equals 12, that means x plus 8 equals 12, or x equals 4. So once again, Christine, we have the answer, x equals 4 and y equals 8, or 4 30-second commercials and 8 60-second commercials.
And that's the only answer that will satisfy the two demands of the station manager.
How are you doing with the demands of the guinea pig?
It's taking me a really long time to count these chia seeds.
Oh, I'm not surprised.
Well, it's just like math, you know, Kanwal. Sometimes it seems like hard work, but the results are really worth it.
Yeah.
Anyway, when solving systems of two equations, there are really three possible outcomes. You may have one answer, as we did in this case, or you may find that there are many answers, or you may find that there's no answer at all. Kanwal, what can you tell us about these other two possibilities?
Well, first, let's take the possibility of many answers. When two equations have many answers, then those two equations are said to be equivalent. When you graph them, they will generate exactly the same line. Let's solve these two equations. And first, I'll do them graphically. So I change them to the slope-intercept form. 4y equals negative 3x plus 6, and 8y equals negative 6x plus 12. We want the coefficient of y in each equation to be 1. So I divide both sides of the first equation by 4 and both sides of the second equation by 8. I have y equals negative 3/4 x plus 6 over 4, and y equals negative 6 over 8 x plus 12 over 8. With the equations in this slope-intercept form, I'm ready to plot them on a graph. Euclid, please. Taking the first equation, I start at the y-intercept of 6/4 or 1.5. Then I plot the next point using the slope, which means, in this case, going down 3 and over 4. Then I join the 2 points with this blue line. Now, I'll plot the other equation on this same grid to see how they fit together. In the second equation, the y-intercept is 12/8. When we plot it, we notice that although it is written differently, it is exactly the same y-intercept as in our previous equation. Next, using the slope, we plot our second point. That means go down 6 and over 8. If we were to connect the yellow points, the yellow line would be identical and overlay the blue line. In other words, all the points on this line satisfy both equations. And so, for these two simultaneous equations, there are an infinite number of correct answers. Any point on the line will be a correct answer.
And we can check this result using algebra, right, Kanwal?
Yes, algebra gives us a very quick way to determine whether two lines are indeed the same or not. It's called the elimination method. When you use the elimination method, you place the two equations one above the other like this. Be sure to align your variables. I have put x's in one column and y's in the other one. When you add them, the results can tell you a lot about how these equations are related.
I'll go over the possible results of using the elimination method, and then you can do an example, okay?
All right.
Okay. When you add two simultaneous equations together, the result can indicate one of 3 things about the solution. 1, that the lines intersect, and there's only one solution that will satisfy both equations. Or that the lines overlap one another, and there is an infinite number of solutions that satisfy both equations. Or 3rd, the lines are different and parallel, and there is no answer that satisfies both equations.
Now, let me demonstrate the elimination method with the original 2 equations. First, I'll convert these into slope-intercept form. Y equals negative 3/4 x plus 6 over 4, and y equals negative 6 over 8x plus 12 over 8. These equations do have the same slope, negative 3 over 4 and negative 6 over 8. Negative 6 over 8, which in its simplest form is also negative 3 over 4. Because they have the same slope, we know that they are parallel. The elimination method will tell you if they are identical or not. Let's try it.
When you add them, you're going to try to eliminate the x's and the y's from both sides of the equation, right?
Exactly, and we can use any of the laws of algebra to get this result. You must start by studying the 2 equations carefully. Look for a way to eliminate the variables. Look at these terms. You will notice that 3 is half of 6, 4 is half of 8, and 6 is half of 12. The second equation is larger than the first equation by a factor of 2. 2 is a common multiple. If I multiply both sides of the first equation by 2, I get 6x plus 8y is equal to 12. If I add these, I won't eliminate the variables. But if I multiply both sides of the first equation by negative 2, then I do eliminate the variable. The reason we use negative 2 is because I want the terms to cancel each other out when I add them. So the terms in one equation will need to be positive, and the corresponding terms in the other must be negative. Now, if I use the elimination method, look what happens. the variables are eliminated and we get the same value on either side of the equal sign. Because this is a true statement, I know the equations are equivalent, or in other words, identical, and they have an infinite number of solutions. We could say it is the same equation in different disguises.
Can you show our audience an example of the third possibility where no solutions exist?
Of course. Let's look at this pair of equations. Y plus x equals 0, and y plus x equals 3. First, I multiply both sides of the first equation by -1. This gives me -y plus -x equals 0. And when I add these two equations together, I get 0 equals 3, which is not a true statement. That tells me that there are no solutions that satisfy both equations.
Let's check this answer graphically. Euclid.
The lines that result from these two equations are parallel. They do not cross, and there are no points common to the two equations. Therefore, we can say there are no solutions for these two simultaneous equations.
So, to summarize, there are three ways to solve simultaneous equations: graphically, or by one of two algebraic methods, by substitution and by elimination, each one used in different situations.
Yes, and each method has advantages and disadvantages. For example, if you're dealing with large numbers, the graphing method may be too time-consuming. And if you try to plot a fraction, the results are only approximate. In those cases, you'll find the other two methods more practical.
But Kanwal, shouldn't we look at simultaneous inequalities?
It's not that different, really. Simultaneous inequalities can be solved in the same manner as simultaneous equations, but the graphing is a little different. Let's do an example. In order to graph these, we first convert them into the slope-intercept form, y equals mx plus b. Negative 2y is greater than negative x plus 4, and y is less than or equal to negative 3x plus 3. To isolate the y in the first inequality, I divide both sides by negative 2, which gives me y is greater than 1/2 x minus 2. Notice that I change the sign from greater than to less than. Remember, whenever you divide or multiply both sides of an inequality by a negative number, the inequality changes. The second equation is fine as it stands because y is already isolated. So now we can graph them. I'll start by graphing only the first inequality. Euclid, we plot the line as if it were an equation with its y-intercept and its slope. But now we come to the major difference between equalities and inequalities. In graphing an equation, every point on the line satisfies the expression. But the graph of an inequality divides the coordinate plane between points which satisfy the expression and those that don't.
That means that for this line, either this side or the other satisfies the inequality. And students have to determine which side gives the solution. That's a very simple procedure. Just select a point above the line and insert the values into the expression. If the result is true, then you can shade above the line. If the result is false, you shade the other side of the line.
For example, suppose I take the point 4, 3, which happens to be above this line, and substitute it into the first expression, I get the following. 3 is less than 1/2 times 4 minus 2. 3 is less than 2 minus 2. Positive 3 is less than 0, which is false. Therefore, I shade below the line for this inequality. There is one other graphing convention that must be considered when graphing an inequality. When I graph inequalities that involve these signs, the set of solutions includes the points actually on the line, as well as to one side of it. So these expressions can be graphed with a solid line, just like an equation. But if the inequality uses these signs, the set of solutions does not include points on the line. I need the line to define the set, but the points on the line are not part of it. And in graphing, I show this by using a dashed line. So any point below the line satisfies this equation. Now let's look at the second inequality. Euclid, erase the first graph. Now give me the line graph of the second expression. Using the same point 4, 3, to test this line, I get positive 3 is less than or equal to negative 9, which is false again. So it too is not part of the solution.
Therefore, we again shade the other side of the line for this inequality. Now the symbol in this inequality is less than or equal to. This means that the points on the line are also included in the solution. So the line in this case is a solid line. Okay, now we can graph these two simultaneous inequalities by placing them both on the same grid and seeing where they overlap. Every point in this region where the two shaded areas overlap will satisfy both inequalities.
Whenever you solve a real-life problem with mathematics, it's very important to apply a little common sense to your final solution. Let me show you. Christine, I believe you've got a good example.
Yes, I do. It's a problem about elevators and the number of people it can safely carry. Now, many elevators have a capacity of a metric ton, or 1,000 kilograms. Now, suppose that C, number of children, each weighing 35 kilograms, and A, number of adults, each weighing 75 kilograms, are on an elevator. Our task is to find an inequality that asserts that the elevator is not overloaded, and then graph that.
Yes, the expression for this is 35C plus 75A is less than 1,000. In the sense of pure mathematics, this is correct, but the practical reality would be better reflected by a series of simultaneous inequalities. Could you show us that on a graph, Christine?
Sure. Euclid, run elevator problem 041.
Here is our graph, and theoretically, any point below the line answers the question. But let's get real here. There is no such thing as a negative number of children. So let's change the graph to reflect this. The inequality for this is C is greater than 0. Likewise, we cannot have a negative number of adults either. So we should adjust the graph accordingly. The inequality for this is A is greater than 0. Finally, there are no fractional people. They only come in units. So the graph should only show points that represent C children and A adults as whole numbers. This requires one final adjustment. And now we can say that the graph reflects reality, in that every plotted coordinate is a real solution to the problem. It's just a little reminder that applying algebra to real life often takes more than computational skill. It takes common sense too.
Thank you, Kanwal, but you know we're out of time.
That's it? But what about the guinea pig food?
Well, you know, I'm sure I mixed the right proportions, but...
But what?
Well, I think Sherry gave me the wrong recipe because this stuff looks a lot like her granola.
Or maybe she eats guinea pig food for breakfast?
Well, I wouldn't put it past her, but listen, we really are out of time. So, tune in next time to the Math Shops, where mathematics isn't just a living, it's a way of life.
Bye for now.
Yeah, bye. I gotta phone Cliff. Hi, is Cliff Gifford in, please?